My name is Vasily. And first of all, I would like to thank the organizers and the people who actually made this possible, and for the opportunity for me to present our recent results. This work was done together with Alexander Cheperno and Dmitry Meshkov. So they are part of the Ergo team, and I'm working in the organization named Research Institute right now. Also, many thanks for the people whom we had discussion with. So this is our recent studies on proof of work, on non-outsourceable puzzles and how to make it. First, let me address the problem we are trying to solve. So here are 3 pie charts. Those are hash rate distributions over the huge open blockchain networks, namely Bitcoin, Ethereum, and Zcash. And as for November of this year, and as one can see, only a small amount of pools hold a huge fraction of the hash rate. That actually means that the attacks of 51% or something like that are, in principle, they are possible, and the stability with respect to those majority attacks is not strictly speaking, no more a feature of the consensus, but a feature of a kind will of the pool holders. So we'll try to discourage the pool mining and joining in the pools. And this will be the subject of my talk. But first, the outline. I will first remind a few things that probably everybody knows already about the proof of work. Then I'll just say a few words about previous results on non-outsourceability. Then I go to the description of our scheme. So that's a recent study. It will be pretty much technical and cryptographical. Well, I first say a few words about the intuition behind our scheme, then present the scheme, provide some arguments to convince you that the thing we get really is what we're trying to make, and then provide a few examples. So first of all, what is proof of work? Well, probably everybody knows. It's a lottery just to determine which of the participants of the network has a right to submit a new block. So every miner, we call them workers here, gets its own puzzle instance, and they are trying to solve this puzzle. The one who successfully solved the puzzle first has a right to submit a new block, and his new block will be included in the blockchain with a high probability. The puzzle is constructed in such a way that the time variance of for the solution is quite large. That is needed in order to reduce the probability of generation 2 blocks simultaneously. So on the left plot, there is a probability density of finding one solution versus time. On the right plot, there is a time interval between 2 solutions. So suppose we found one solution, and what is the probability that the second solution will be found by the network within some time? So the point of that huge time variance of the block arrival time is the really small probability of finding 2 blocks simultaneously within the network synchronization time. Usually people use some trial of pseudo-random numbers. So in general, it can be written as some function of some message, which is normally the block header, plus some nonce is lower than some target value, which is used to adjust the difficulty to keep the block generation time constant on average. Well, nonce can be a subject for additional conditions. For example, you can fix the length of the nonce or require some additional properties of it, but we'll talk about it a bit later. So now, how the outsourcing works, how the pool organize the puzzle solution. The pool takes some initial data to generate the puzzle instances from the blockchain network and acts as an outsourcer. It performs no work, it just distributes the puzzle over the workers, and the miners try to solve those puzzles. The miners send back the solutions and shares. Shares are almost solutions. They are needed to estimate the amount of work which are performed by miner for the distribution of the rewards. So shares are solutions which are just not good enough to generate the new block, but but still they require some computational effort. So the outsourcer submits a solution to the blockchain network, gets the rewards, and later distributes the rewards over the workers. And now to our idea, what will we try to do? So the point here was that the outsourcer can claim the rewards, and the workers, in principle, they cannot. So the solution routine is disentangled from the reward claiming routine. And our idea is the following. So what if we somehow allow workers who actually solve the puzzle to claim the rewards? So in a sense, if a worker obtained a valid solution, he somehow can send a transaction and try to spend the block rewards somewhere else. And here we come to the race condition between the pool holder and the worker, and there is a significant probability for the pool to lose all the rewards, and the reward will go to the worker who actually performed the puzzle solution. How can it be achieved? Well, we can try to embed some secret data in the puzzle solution. Well, for us, the valuable secret data is, of course, the spending key for the block rewards into the puzzle instance in such a way that solving the puzzle without the secret data is very inefficient. So in order to efficiently mine then the next block, you need to have a secret key, and the secret key will be later embedded, and the public key will be embedded in the solution, such that the network can see that the one who actually provided the solution has a right to claim the rewards. Well, there were few previous works, and the ones I'm aware of, probably there are some more, but those started with the work of Miller, Kosba, Katz, and Shi, and they proposed actually the definitions for non-outsourceability in strong and weak forms. And for strong non-outsourceability, they constructed a solution to the similar problem that we have, which relies on zero-knowledge snarks. This is good, this is provable, but the drawback of using zero-knowledge snarks is a big size of the solution. So once you get to the snarks, you automatically increase your validation time, and you also increase the solution size up to the scale of, let's say, 10 kilobytes, which is, if we are talking about synchronization with the block headers on, say, mobile device, well, 10 kilobyte per block header is already a significant number. Another work from 2017 is another idea, is a part of work concentrated on a slightly different subject on distributing the work piecewise. Although the idea is formulated as following: why not we try to just, instead of using some pseudo-random numbers, try different signatures. So you generate different key pairs, and you try different signatures, and you require something from the signature. Let's say the hash of the signature is less than some target value. If we assume that you cannot sign some message without having a secret key, that pretty much works. Although the drawback here is this construction looks quite specific. So you cannot replace the signature with something else, and it covers only a limited amount of puzzles. And the third work, which is with idea very, very similar to the previous one, I believe those two were developed independently, but it also relies on the signature-based approach. Okay, now let me describe the intuition behind our idea. So we start with a general proof of work, let's say for a hash-based function for now, and then we'll extend it a bit. So suppose f is our hash function, which acts as a random oracle, and we are trying different nonces. So m is a block header, n is a nonce, and z is a target value. We want to incorporate some secret data in the solution, so we'll try to make it the following way. The puzzle solution will work over numbers, let's say modulo some prime, and the validation will work over some cyclic group with hard discrete logarithm assumption. So starting from this point, we can translate it into some cyclic group G large with a generator G in the following way. So in principle, one can do the validation of this condition in the group, although it barely makes sense for now. So one can disclose the value below the target D for the given hash, the nonce, and in principle, instead of doing the comparison on the client side between the values of the numbers, you can do it in the group. So, moreover, what is so special about the zero value? So we look for some nonce which gives the hash which is within some proximity to zero. There is nothing special about it, and we can choose, instead of zero, we can say, let's look for the solutions which are close to 100 but instead of zero. And this number is pretty much arbitrary, and we can use it as some secret data. So we'll generate a key pair, a public key and the secret key will play the role of let's say zero, or the replacement of zero. We'll search for the hashes which give values close to our secret key for now. So our offset or our mismatch, when we try hash, we don't get exactly to that value. We get to some value, secret key minus D or secret key plus D. And one can also disclose it, so the verification can be done over a cyclic group, let's say some elliptic curve, or I don't know, multiplicative group of the finite field. And the disclosed part is our message, which is block header, public key, nonce, D, our offset, and the puzzle is getting close to our secret key. So validation can be done over the group, but now if you look at it, for now, that secret key is not actually secret because it's trivially disclosed by the provided data. So let us think a bit more, and we'll see that during that validation, actually what is being disclosed is one linear relation between some numbers. So actually the line with g to the power of f of something and the line in the bottom, they're equivalent. So given that verification routine, we automatically disclose one linear equation. And if we have only one secret variable, then this equation can be solved. So the conclusion is, if we try to add one more hidden variable, or as one more secret variable, then the verification process will reveal only one linear relation, and we will get one equation with two variables, which we cannot solve in general, and we will leave the same security as for using one key. So let us do it in a spirit similar to the one used in Sigma protocols and Schnorr signatures. We generate one more key pair. So X is a secret key, W is a public key. We commit to them with our functions f. Let's say note the 0 and 1 in the end, so they are linearly independent and we don't have the connection between the terms. And now our puzzle is getting the number on the left-hand side, with which within the random oracle model should be distributed uniformly close to the 0 value. And the solution which a miner can provide consists of two public keys, pk and w, the corresponding value of nonce and the value of d. So the validation of this solution can occur in the group, and it's quite straightforward. We just exponentiate the equation above, and this equation is pretty much the only data which has been disclosed. So there is no option of solving this system with this one equation for two variables when x and sk are unknown. So in principle, sk already can be used as a spending key for the block reward. So now we come to our scheme. In general, the scheme for puzzle solving looks in the following way. As an input, we get the message, we get the target value z, and the key pair, secret key, public key, which will be later used for the spending. N large is a list of nonces, which we first assume empty, and then until we get something in that list, we generate the new secret key x, which will be later committed via those functions, and try to solve this puzzle over the number. The function solve returns the list of the nonces which solve our problem. And as a part of then we calculate our offset d, which should be less than the target value, and return our public keys, nonces, and offset together with the solution. So the solution verification can be done over the group. We first check that the puzzle was actually solved. We require that the nonce is some valid nonce, so it fits into restrictions we put on it. And finally, we just check that the puzzle was solved over the group. So when the discrete logarithm problem in that group is hard, we are pretty much safe. So now a few words about actual non-outsourceability. I will try to provide just a sketch of the arguments which we can talk about using that notion. Well, first, the pool cannot outsource. The first idea which comes to mind, well, if the problem can be solved over numbers, why can't it be solved over the group elements? So suppose the pool just provides the worker with two public keys and says, okay, solve, and the block header and says, okay, solve that. Well, actually, it's quite easy to see that if there is a significant fraction of public keys for which the worker can solve this problem, then the worker actually can compute discrete logarithm over that group, because it can pre-generate one of the public keys itself, and hence this group is not suitable for any use in cryptography anymore. But what if the outsourcing is possible not using public keys, but using some additional information? And the claim is that we have even stronger, slightly stronger arguments. So, for example, suppose that the pool has made some mixture of the data and provided it to the worker, and it can incorporate some parts of information over the secret keys and whatsoever. So the claim is, if a worker can produce in a plain text the solution, well, probably it's safe to assume that a worker can somehow produce, well, couple solutions or couple shares if the solutions are too hard. But once the worker can provide two valid shares and the worker knows which offsets they correspond to, the worker has actually two linear relations which are disclosed under the verification. And actually, what the worker gets is a system of two linear equations with two variables, and the secret key can be trivially reconstructed, so that the general picture looks as follows. The worker has, let's say, a public key and a secret key, and the solving routine requires at least secret key, or actually both. And the solving routine can provide few solutions. Those can be not even the solutions, but those can be valid shares. And taking just one of the solutions, there is no way to determine which keys were used. But taking the two of them are already enough to reconstruct the secret key. And the rewards can go to the public key, which is disclosed as a part of the solution. Let's look for an example right now. So suppose instead of claiming 0 and 1 index as a postfix in string concatenation, I just put it here as a subscript to f, and f to hash functions. So we can make the hash-based proof of work out of it, just setting the set of nonces to a single value, and the problem will be just trying different pairs of public and secret keys, almost the same as with trying different signatures, and that's good. But as we can see, instead of nonce, we can try different keys, check the hashes, and solve our puzzles in that way. So how can we use nonces? It looks like for just pseudo-random number trial, the nonces are not needed. Well, in principle, we can put some constraints on nonces and incorporate a bit more complex problems than just a pseudo-random trial in the nonces. So pseudo-randomness with respect to the field n is not needed. In fact, we can make it different. We can try to arrange our puzzle in the numbers modulo the group order, and suppose n now the valid nonce is a list of k numbers, and our functions are just sums over hashes over the sublist of these numbers. What we got now is the following problem. There is a list of numbers, r, which are just obtained from the line above. And within the random oracle model, these numbers are just pseudo-random uniformly distributed. And we search, those numbers are modulo our group order, which is large Q, and we search for a sublist, which is close to 0. So we just converted the k-sum problem to the non-outsourceable form, which can be used in the proof of work. The k-sum is pretty much analogous to k-XOR, which is used in equihash. Although there is slight difference, because in equihash, people use algorithm binning. There are a bit more conditions on the solutions. So not every solution which XOR to 0, which provide a k collision, is a valid solution for equihash. Although thank you. Although the scheme can be converted to incorporate all those conditions. So now about the practicality, which is claimed in the title. Let's sorry, just a few words. In principle, we can remove k from the previous slide and remove the restriction on the length of the list, and we'll get subsets some problem, which is also interesting. It seems that the class of the puzzles which we can make non-outsourceable is very broad. So now about the practicality. So what is the overhead in comparison to outsourceable default version of the puzzle? Well, first, the miner should generate 2 key pairs on every round of the puzzle. It doesn't seem a lot of work. The verifier has to perform 2 exponentiations in the group and a couple of multiplications, which is also reasonable. And the disclosing of public keys and offsets actually increases the block header size. Well, suppose we use 32 bytes elliptic curve cryptography, then the additional load will be 33 bytes for every public key that that makes 66, and 32 bytes for our value of D, our mismatch, which sums up in 95 bytes for the worst case when we have target which has the same bit length as the secret keys. And this actually sounds usable. Additional 100 bytes for block header, this is already good to have. And just to sum up, as my colleagues are the part of the Ergo team, we are trying to incorporate it in the proof of work for the developed blockchain platform. Well, it's some analog of the subsystem, although it still undergoes testing and quite an intense discussion. So, and to conclusions. Well, first, we proposed a new scheme to convert proof-of-work puzzles to non-outsourceable form. We were trying to discourage pool mining, and the worker, in principle, the worker who performed the solution can claim the reward. If the worker took the job from the pool, it can steal the money from the pool with significant probability. As for the structure of the puzzle, as you have seen, the structure of the puzzle can be quite generic by using this nonce structure. But even if you forget about nonces and just look at the hash function structure, it pretty much doesn't matter which hash functions we use. So they can be memory hard, they can be ASIC resistant, or if you come up with some computationally hard puzzle which is a bit more sophisticated, it can be included into nonces, then you're fine. You may have slightly larger overhead or the number of group elements which you disclose, but it's still doable. And the overhead and the block header size is around 100 bytes. So the corresponding costs are low and it seems quite practical. So the particular version of the protocol is under testing. Thank you very much.
Great, thank you, Vasily. We have time for questions. I see some questions at the back.
Yeah, isn't any verifiable random function construction going to give you this?
Any verifiable, sorry?
VRF construction, like BLS signatures, RSA with FDH, or NSEC5,
okay.
all of those.
Okay, so you're talking about the formal analysis and the proofs, or like equivalent of security we have. Is it the question, or?
Give you the underlying property that you have to have the secret key to do the thing that you're going to be calling your proof of work.
So in principle, we are similar to the level of security of Sigma protocols, although those are not exactly the same. So we are working on the proofs. There is one version which I didn't present here, which has similar properties to Schnorr signatures. Although the problem with that is that probability of key reconstruction depends on the target, which is bad. For the current construction, we are working it out, and so far it seems that the security level is the same as just one secret key.
So you probably should look at the NSEC5 construction from DNSSEC, and it gives you probably what you want, and it already has security proofs.
Thank you.
Time for just one more question.
So you're using the discrete logarithm problem, and I was
Right.
wondering if the same construction carries over to other hard problems.
In principle, yes. In principle, yes. So what we need from discrete logarithm problem here is the homomorphism. So we need to perform additions both over the numbers and convert them to multiplication in the group element. So anywhere, if you have some module over the ring of, let's say, integers modulo something, if you have module over that which is secure, you can convert it. You don't need homomorphic multiplication, but addition will suffice.
And people seem so keen to discuss this. We'll do one more question at the back there.
Yeah, I just had a question. You introduced this with like the dangers of pooled mining and saying, okay, now here's a proof of work that cannot be pooled. But people pool mainly to avoid, like as an economic necessity to avoid variance. So you introduced this new technology where you can no longer pool. Wouldn't that actually do the opposite of discouraging small miners and leave you with fewer big players?
That's debatable, but in a sense that's an issue. That's a problem that the variance for the rewards for the ordinary miners becomes hard. But in contrast to that, it's not in a sense what we are doing in Ergo is not worse than what we have now. So in order to put the rewards on the public key attached to the solution, you need a special kind of output, let's say miner can spend, call it that way, so that you cannot change that transaction within the same block. And once the emission goes to the public key attached to the solution, and you have no choice, there is the pools are discouraged. But once the emission is over, the clients can put their fees, and they can choose between miner can spend and, let's say, pay to true condition, the condition which always holds. If the network decides that it's not needed, they can always say, okay, instead of paying fees to miner can spend, I can pay fees to true, and then just anybody who actually provided the block takes them.
So clearly plenty to discuss there.
In a sense, we incorporate what already existed and give the choice.